Okay, good morning, everybody. Thank you for attending this webinar about ANSYS Mechanical as an essential tool for semiconductor and hardware startups. My name is Jose. I'm the Fluid Codes Technical Manager, and during around 2 hours, we're going to talk about how to use ANSYS Mechanical for the semiconductor industry. So let me just open the next slide, actually. Just 1 second. All right, so good. So basically, I will show you the agenda in some slides later, but there is like 3 parts for this webinar. The first part is just to show you an introduction about Fluid Codes, about ANSYS, as well as about the Startup Fund, which is an organization which is based in Lebanon. The founder of this organization will give you more information about it. And also, I would like to talk about the startup program from ANSYS, which will facilitate or make things easier to start to use simulations for those companies which are starting with their business. So this is actually the agenda. As I mentioned before, we have the first kind of introduction. Then it will last only for 15 minutes or so, and then we will be focusing the main part of the webinar, which is to see how we can use ANSYS Mechanical for the semiconductor industry, and we are going to emphasize a lot in cases related with PCB boards, as well as MEMS, actually, micro electromechanical systems. After that presentation, which is going to be purely technical about ANSYS Mechanical, what I'm planning to do is just to show you for around 30 minutes. I want to do an on-live demonstration about the software for a PCB, actually. And then if we have enough time, I will go further and I will show you a couple of cases more. Then we will end up with some question and answers. So since we are not that many people, actually, we might be able to do it directly speaking, actually. So just posing your questions. But if we see that as long as the webinar progress, there are more people, then I will tell you to just type it in the chat and we can deal with them directly. Also, if you have any question at any time, please you can just type it in the chat, and in the end we will discuss them. All right. So first of all, who is Fluid Codes? Fluid Codes is the ANSYS elite channel partner in the Middle East, and we are now we just 1 year ago opened another office in the east of Europe, in Bulgaria. So currently we have 3 offices: one in the UAE, as I said, in Dubai, another one in Saudi Arabia, and another one in Bulgaria, in Sofia. So we are the representation of ANSYS here in the territory, in the whole Middle East, including obviously Lebanon. And we have a team of engineers who are focused in simulation. So basically we are dealing with training, we are dealing with support, we are dealing with consulting as well. So we are actually covering and only focusing in ANSYS, by the way, we are covering the whole territory of the Middle East with this team of engineers as well as sales representative. Obviously, we are totally connected with the rest of ANSYS centers around the world. So basically, we have a very good collaboration with ANSYS India because of the proximity, actually. Also with development in the US, and obviously with Europe because we have traditionally been linked with UK. If you want more information about Fluid Codes, you are more than welcome to visit our website, fluidcode.com, where you will find more information. You will have find successful cases about ANSYS, information about training, services, products, etc. All right. So regarding the startup fund, maybe Raja, if you can hear me, if you can just unmute yourself.
Yeah.
yeah, you can just give an introduction about your organization, please.
Okay, can you hear me now, Jose?
Yeah, perfectly.
Okay, great. So I want to say good morning again, and thank you for this introduction and for the webinar. And I would like to say that Startups Fund, it's an organization that supports the hardware ecosystem in Lebanon and later the MENA region through providing workshops and webinars. And we're gonna keep on working on this. In addition to that, we have built partnerships with hardware accelerators like LA in Los Angeles, and as you know, with Fluid Codes to provide some of the workshops that we're going to work on during the coming years. That's it.
Great. Thank you, Raja. And actually, I wanted to thank you in the name of ANSYS and Fluid Codes for the great job you've done with these webinars. We will later on mention other webinars who are gonna be coming later in the next months. But I would like to personally and in name of Fluid Codes and ANSYS for the efforts you are doing for promoting ANSYS, especially for startups in Lebanon. Thank you very much.
Sure, you're most welcome.
Thanks.
It's my pleasure.
Great. So, okay, let's continue with the rest of this first presentation. So, obviously, we are talking about Fluid Codes, we are talking about the Startup Fund, but also, and actually the most important part here is what is ANSYS. So, ANSYS is nowadays the simulation leader in the industry. ANSYS is focusing developing software, basically. We are in the NASDAQ, so we are a trusted company in 96 on the top 100. There are more than 2,700 employees, direct and indirect, and the presence is in around 40 countries and more than 75 locations. Actually, in terms of the competition, we are the largest software developer right now, which 3 times bigger actually than the nearest competitor. So ANSYS actually is everywhere, I would say. Let me just go to the next slide. If you think about any product, most probably now you have one in your pocket, actually, like a mobile. So the idea of ANSYS is to enable customers or companies to predict with confidence that their products are going to be actually working as they are intending to do. So I will come back to this later on in the next presentation. But the idea is that instead of performing physical tests, which are really expensive nowadays in the industry, what we are going to do is to simulate them in a virtual environment. So this way, instead of let's say performing a test of 100 of different designs, with ANSYS we will arrive to the conclusion of 2, 3, or even less, and these will be the ones that you might need or not to create a physical prototype test. So ANSYS has a breadth of technologies. Obviously, in this presentation or in this webinar, we are going to cover basically the mechanical part. But as I said before, we will have another 2 webinars basically for fluid dynamics, for CFD, computational fluid dynamics, as well as for electromagnetics in the semiconductor industry. So the reason why we are having them is because ANSYS has a range of products from CFD, single cases or more advanced ones, structural mechanics, which is the one we're going to focus here, from linear statics so to more advanced high-speed impact, for example, electromagnetics from low frequency to high frequency, etc. And also from the systems point of view. So the system part will be covered as well as in another webinar. But we are able to simulate the whole, let's say, multi-domain system inside ANSYS. Obviously, we have a huge number of customers nowadays. You have here just a small representation of one of the most important, actually. As you can see, ANSYS is a general purpose software, which means that as long as you are able to draw your geometry, you can simulate it. It's not a software only for oil and gas. It's not a software only for nuclear or for turbo aerodynamics, for example, or automotive. As long as you are able to draw the geometry, you can simulate it, providing you know your conditions. So here you have just some of the customers actually, or companies who are actually using ANSYS worldwide. By the way, these two presentations, and also we are recording actually the webinar, so we will send you all attendees this webinar, so later on you can have a look more specifically in certain customer or certain slides that you are more interested in. From the high technology companies, you can see that obviously in the semiconductor industry and as well as mobile, communications, consumer electronics, the most important actors, I would say, from these industries are also using ANSYS. So basically, well, Apple, Samsung, HTC, HP, Amazon in the consumer part, AMD for semiconductor, Intel, NVIDIA, all of them are using ANSYS in an extensive manner for electronic devices. So what is the idea of ANSYS? If you go back to 2005, and even I would say earlier, the idea was that maybe, okay, 1 out of 22 engineers were using ANSYS. But the trend that we can see with the years, as long as the computer resources are getting better and improving and making more powerful, we can see already that in 2015, let's say that 1 out of 6 engineers were actually using simulation. But if we go further, our vision is that by 2020 or even earlier, all engineers in an organization will be able to use simulation up to some extent. Okay, so this is the vision of ANSYS, and that's why if you go to the ansys.com website or even to our website fluidcodes.com, you will see that there are many products nowadays oriented to many type of departments in the industry. So that's why we believe that ANSYS is going to fit in different departments, and not only for analysts as well. Okay, if we talk about the startups, because actually this webinar is, our intention was to address it and to focus more in the startup industry. We are aware in ANSYS that, okay, once you are starting with your business, obviously the budget is going to be one of the limitations. But from the other side, you want to start to maybe create a new disruptive technology, which is going to change let's say the ecosystem. So that's why ANSYS decided to start or to create the startup program, where I'm gonna discuss them with more information in the next slide. Where right now actually we have over 240 startups in this program, and actually this number is continuing growing week after week. So what is actually this startup program, or which are the benefits? First of all, you will have the industry leader, obviously, in terms of simulation. So you will have access to the whole ecosystem for mechanical, for fluids, as well as for electromagnetics, in order to perform your full analysis of your system. From another side, you will have access to the largest simulation company in the world, as I said before, with more than 450 PhD level engineers working in support, as well as a lot of more engineers working in development and support for your cases. Obviously, we intend with this program that once you start to use the software, you will reduce your cost. So as I said before, you will reduce the manufacturing, materials, warranty, and prototype testing, actually. The idea obviously is that you will reduce your time to market, so because it will have an impact in your design of your prototype and in the timeline, obviously. And obviously you are accessing to a well-validated software around the world, as I showed you before with the previous slide with our biggest customers in the region. So you will have access to a validated technology, which is proven nowadays by, as I said before, a huge number of customers in the world. So there are some criteria for this startup program. The first thing is that it has to be a privately held company, so it's not for public companies. it is intended to companies who are developing products, so no for those companies who are providing services like consulting. It needs to have less than 10 years, the company, as well as less than 5 million US dollar revenue per year in the moment where you just apply for the program. There are some marketing commitments that I would like to explain in the next slides. You might be willing to make an exclusive use of ANSYS product for simulation work. Okay. It cannot be a pre-existing ANSYS customer, obviously, because it's intended for startup companies who are starting with simulation. Obviously, it cannot be a new division of a pre-existing company. It has to meet the standard ANSYS export compliance requirements. And the idea is that there will be a minimum number of engineers who have bachelor's or at least master's or master's degree who are willing to invest in training for learning how to use the tools. Obviously, it's a engineering simulation tool, so your engineers will need to be trained on the software. Okay, once you are eligible to this, let's say, ANSYS Startup Program, once you are inside this benefit, you will have access, obviously, to all products. So basically, you will have access to a structural and fluids bundle if you want to go only for mechanical, if you want to go for CFD, IM for designers, etc. Also for embedded software like Skate, which is used for creating code based in different standards. Electromagnetics bundle as well, that we'll mention a little bit later on. So you will have access to this product. In terms of requirement, well, the first thing we are asking for whenever you are eligible to this startup program is to place your logo in our website in ansys.com/startups. Also, we will release a press for advertisement once after 1 month within the joining, once you join the program. We will ask you for a testimonial, so we will give you some ANSYS template, so you can just say, okay, I'm starting with a startup program and I'm doing this kind of simulation right now with my product. We are going to ask you for trying to promote the startup programs in different social media. And also we will give you some, let's say, exposure to our in our ANSYS website, ANSYS blog. We have also Advantage magazines. So we will give you some exposure here, so that also it will be great for your actually for advertisement of your products. And we will mutually agree in some ANSYS events, for example, in here in the Middle East. So maybe we will invite, you might be invited to collaborate and to present and just to explain to the rest of a startup and audience about your experience with the startup program. Just to give you a couple of companies, one of them is One Wheel. This is a startup which is eligible to this startup program. Actually, they are already simulating and using ANSYS for their skateboard. So they wanted to do something different. They wanted to do a skateboard with one wheel, with battery inside, in such a way that they can go in any type of environment. So they asked ANSYS to start with this startup program, and actually now they are performing simulation to optimize their product. Another company, this Carbon Freight, basically they wanted to reduce or to make 18% lighter their cargo containers. So they were eligible to this startup program, and now they are performing simulations with ANSYS with the mechanical bundle. So this is another great example of startups who are actually using the software with a much minor cost and already performing their simulations and optimizing their products. Obviously, if you want more information about this startup program, you can just contact us. You can go to startups@fluidcode.com. Also, you can go to the Startup Fund organization in Lebanon through our fellow Raja Jones, and you can just ask us for information. We can evaluate case by case, obviously, and we will determine if you are eligible, and so we will determine how much is the cost and how we are going to start with the process. All right, so this is everything for the first part. So as I said before, we are going to focus now in the discussing different applications where ANSYS Mechanical is used in the semiconductor industry. So for the almost the next hour or so, we are going to focus basically in ANSYS Mechanical. So this is what we are intending to do or to present in this part of the webinar. So first of all, we are going to discuss about what is engineering simulation, and after that, I want to give you a brief of the three types of analysis actually that nowadays our customers are using simulation for. Then we will discuss different types of multiphysics analysis that we can perform on PCBs. And after that, I want to show you like the typical thermomechanical analysis which is done in a PCB. Okay, this is quite important and it's quite used nowadays by our customers worldwide. So that's why we wanted to focus in this thermomechanical type of analysis that is so important in the industry. Then actually I wanted to include also these micro electromechanical devices or MEMS, so that it can give you an idea or it can give you an overview about how to use ANSYS for these micromillimeters devices, and how ANSYS is used for actuators, for microbolometers, etc., in case you have such a type of applications. Then we will end up with some conclusions, and after this presentation we will focus in the demonstrations. So if we want to understand what is engineering simulation, the idea with engineering simulation is that we will use our computers in order to get the response of our system, okay? In a virtual environment, obviously. So instead of perform product tests, what we want to do is to reduce the amount of product testing. This is one of the ideas of one of the most important reasons why we will use simulation. Also, we want to simulate some designs which are not suitable for prototype testing. There are some cases like, let's say, for example, you want to evaluate the launch of a rocket in the out of the Earth, for example. It's almost impossible to create a prototype test of this case. So in those situations, you need to simulate it and get a better understanding about this, let's say, launching of the rocket, for example. So not everything can be actually created a prototype. To create more reliable and better quality designs, obviously, because now you will get information about your whole systems. It's not like when you are doing a prototype testing that, for example, wherever you place different proofs, then you will be able to get information. Now with simulation, you will get information in your whole model, in any part actually of the model. So the basic, and I will say not the basic, the most important part of engineering simulation will be to save cost. We will perform less amount of product tests, or even we will remove product tests from our design stage. So that way we will save a lot of money with simulation. So in order to talk about simulation, there are three types of physics that can be analyzed. The first one is what we call structural mechanics, also known like finite element analysis. So everything related with the solid part, everything related with how structures behave when they are subjected to structural, thermal, electric loads, how they vibrate, everything which is related with the solid part will be simulated with what we call structural mechanics. But there are situations where also we need to take into account the fluid surrounding our structures. For example, in this PCB that you have in this image, you might need to evaluate the cooling process inside the PCB. So in order to take into account or to analyze the dynamics of the fluid, we will use what we call computational fluid dynamics, also known like CFD. So with CFD, we will be able to analyze any problem related with the fluid part. As I will show you later, the idea is that we will couple all these worlds. So in other words, I will use, for example, if we think about a PCB, I will use CFD for getting the temperature profile of the solid part, and this temperature profile will be interpolated in the structure in order to perform the structural part, like thermal strains, von Mises stresses, etc. So even though I'm mentioning these different physics in a separate manner, the idea is that all of them will be connected in a multiphysics environment. All right. If I continue, the third type of analysis that we can perform is what we call ANSYS or electromagnetics analysis. And in electromagnetic analysis, we can take into account anything related with, or we will simulate anything related with the electromagnetic fields. So let's think about power integrity in a PCB. Let's think about signal integrity. Let's think about antennas, radio frequency, microwaves, low frequency cases like a transform. All these type of situations which are involving electromagnetic waves will be simulated by performing electromagnetic analysis. And the good news on this case, as I mentioned before, is that ANSYS has the whole portfolio for this type of analysis. So how is the workflow actually whenever we deal with simulation in ANSYS? First of all, we need to create a geometry. So we need to have a cut or a representation of the geometry. It can be done outside of ANSYS, or it can be done inside ANSYS. We have both options. And the idea is that once we have the geometry created, we will create a mathematical model, also known like we will create a mesh. And then, depending on the analysis, we will perform mechanical analysis, we will perform CFD analysis, or electromagnetics. And all of them, as you can see with the red arrows, all of them will be connected. So ANSYS is nowadays the only software in the industry which has the capabilities of performing all these three types of analysis in the same environment. So no need of exporting results from one analysis, importing another one, using different tools. No, this is something from the past. Now everything is connected through our interface, which is called ANSYS Workbench. So once the simulation is done, we will post-process, meaning we will evaluate temperature profiles, we will evaluate currents, we will evaluate stresses, etc. And then we will optimize. So meaning that we will say, okay, I want to have the maximum temperature in this part of, I don't know, 30 or 60 degrees temperature Celsius. So let's change the boundary conditions so that this, which is my target, is matched. So this is what we will call optimization. All right. So let's think now about PCBs. Since we are focusing in the semiconductor industry, as most of you are aware, PCBs is a key point, or is a key part of structure or devices that we need to design properly. So let's focus now more on PCBs actually. So first of all, PCBs by nature are multiphysics. By multiphysics, I mean that all type of simulations that I described in the previous part are eligible, are applicable, or can be applied to PCBs. For example, if we just focus if we just think about electromagnetic, we may have a PCB where we need to calculate the power map, okay? Or we might need to calculate radiation, interference, current densities. So this is what we will calculate, and we can calculate with an electromagnetic simulation. Okay, but the thing is, these currents will be causing, because of the Joule effect, an increase in the temperature in my PCB. So I need to somehow, these current densities, which are going to be calculated in the electromagnetic part, I need to import them in my computational fluid dynamic analysis, where I will be able to take into account different gases, different fluids surrounding my structure. So because of the convection with the surrounding air, in this case, in this PCB, I will be able to calculate the temperature profile in both the solid and the fluid domain with computational fluid dynamics. Obviously, the more my parts are heated up, it might have an influence also in the power map. So this will be what we call a two-way fluid structure interaction, where both physics, electromagnetic and CFD, will be communicating the same time till we arrive to the final contour of temperature of my PCB. After that, once I have my temperature profile in the PCB, what I will do is to import it automatically in ANSYS Mechanical, and I will be able to calculate thermal strains, I will be able to calculate von Mises stresses, and so on and so forth. So as you can see, the whole design of my PCB requires a multiphysics solution, starting from electromagnetic analysis and ending up in the mechanical part. So as I said before, the intention of this webinar is to focus basically in the mechanical part. So I just want to give you some overview, a few slides about the other two parts, and we will have in the next months, we will have new webinars where we will deal or we will talk about electromagnetic analysis as well as computational fluid dynamic analysis more deeply. So for this part, I just want to give you a quick overview about each of the other two before going more deeply in the mechanical part. So if we think about electromagnetic simulations only, okay, we have any type of analysis that can be done there from the low frequency point of view to the high frequency part. So ANSYS has a bunch of products which are gonna deal with this type of analysis. So if we see the trends actually in the electronics industry, we can see that, okay, miniaturization is one of the most important part, okay? So if you think about, I don't know, the first cell phone, which was invented in 1973, the weight was around 2 pounds. And if you take into account now any of the modern iPhone 6, for example, we are talking about 4.5 ounces, okay? And before you were able only to talk, actually. And now you can send emails, you can be connected with other people directly with a chat. You can enter in internet, actually. So miniaturization actually is one of the key points that actually the electronics industry is going through. If we think about mobility, wireless connectivity, we need to have well, if you think also about 12 years ago, actually, let's say 3% of the population maybe were using cell phones. Now every single person has at least one mobile. So you can imagine how many antennas, how do you need to keep the communications with all these devices. Now also thinking about the IoT, Internet of Things. Customers are asking for faster communications. Now we have 5G, which is coming as well. From the other side, we need to have more efficient batteries as well. We need to have embedded software. So all this is something actually which it's a cycle where obviously simulation is part of this design. If you think about a mobile, for example, we have different type of analysis from the electromagnetic point of view that can be performed, from signal integrity, for example, from power integrity, touch screen, electromagnetic interference, electromagnetic communications, antennas. All these later on we will need to couple with thermal behavior, as I said before, vibration, stresses. So this is something actually where we need to simulate it from the electromagnetic point of view. So ANSYS has the portfolio actually for performing the whole design for the chip package system from A to Z. So starting from analogs, IPs, developing the chips, the whole package for high frequency, for SI wave, for electromagnetic interference. So all these products, all these type of applications from the electromagnetic industry, as I said before, will be covered in another webinar, but I just wanted to give you a rough overview about all type of analysis that can be done for that part. Now, if we focus from the computational fluid dynamic point of view, one of the key points actually where ANSYS is used for PCBs or for electronics industry is for electronic cooling. So for this, there is a specific product which is called ANSYS IcePack, which is an integrated electronic cooling solution for packages, for boards, and in general for electronic systems. It is combined with other packages for importing actually electronic CAD, electronic representation of the geometry. It will allow you to automate, to perform the mesh in an automatic way. It is obviously based in ANSYS Fluent, which is the leader in the CFD analysis in the industry. It has a lot of advanced capabilities. It is linked with the rest of ANSYS product, obviously. So we will, as I said before, we will deal with this in the CFD webinar. But for this kind of simulations for electronic coolants, there is a specific product which is called ANSYS IcePack, which is dealing with this type of analysis. So in this ANSYS IcePack, there is a lot of a vast library of standard electronic components, which will help you to model the creations without having to search for the manufacturer's data sheet, actually, for additional information. It includes a lot of information for material properties, for the fluids, for solids, for surfaces. It has into account fans, if in case you want to simulate also the fan for the cooling of the device. There is a lot of operating curves from these fans, from Panasonic, Sanon, Delta, ABM, etc., for the leaders in these fans manufacturers. It has a lot of filters for like fan air filters, depending on the vendor part number that you want to include for your simulation. So it's completely the tool actually for taking into account electronics cooling. The important part is that even though it's a tool focused in electronic cooling, it is using the best-in-class CFD solver nowadays in the industry, which is called Fluent. So Fluent is a very well-validated software for computational fluid dynamics, and it will obviously allow you to calculate temperature profile by using the conjugate heat transfer, and also it will allow you to use parallel scalability with ANSYS HPC. It has embedded inside, in case you want to simulate the rotating, the moving reference frame, for the fans. So it allows you also to take into account fan inside, as I mentioned before. And also it allows you to calculate the tracing maps. So for example, in this PCB that you can see in the image, you can import the electronic trace as well as bias information from other EDA layout tools. And the software is going to be able to calculate the temperature distribution for the whole printed circuit boards. So actually, as I said before, is specifically the tool for taking into account all type of cooling behavior inside PCBs. Obviously, in the end of the simulation, it will give you the possibility for evaluate contour results, temperature profiles, as you can see here, fluid streamlines. For this, in this case, this is just a graphic card. It will allow you to create reports. So definitively, it will be the tool for electronic cooling, and it will be connected with the rest of ANSYS portfolio. Okay, was just a brief introduction actually for the other two types of physics. As I said many times already, there will be another 2 webinars based on electromagnetics as well as CFD. So from now on, what we are going to do is we are going to focus in the mechanical part of the electronics industry, and we will cover different applications for basically focused in the structural or mechanical part. So what can we do with structural mechanics? First of all, we can perform the most or the simplest type of analysis, which will be like a static analysis where we don't have into account inertial effects, for example, and we are just considering linear behavior. So my material is linear, for example, structural steel, aluminum alloy, before having plasticity. But also we can consider nonlinear effects. So let's say we want to take into account a nonlinear material like rubber, like hyperelastic, plasticity. We can take into account this type of analysis as well. Okay, but this will be from the static point of view. But also we can go and say, no, I want to perform a dynamic analysis, which actually in PCBs, as I will show you later, is going to be one of the key points. So we might be interested in vibrations, for example, or we might be able to do a time history, or something more important for PCBs, drop test. So all these type of analysis, we can perform them inside the same tool, which is called ANSYS Mechanical. Something which is going to be important for PCBs will be to take into account the connections between all components in a PCB. Just think about, for example, this PCB here. You have a lot of components which are glued or which are welded to the laminate, right? So imagine as long as you import this huge number of pieces, obviously you will need to create the contacts between all bodies. This is something that the software will automatically identify all contacts from the analysis, from the design, from the geometry. Actually, I will show you this with more information in the demonstration later on. So these contacts are going to be identified, and something which will be important will be also ball pretensions. So let's say we have a PCB and we have a lot of small bolts which are making that all the laminates, all the layers actually are connected. So we will need to take into account the pre-stress in these ball connections. Okay, so this is something that actually can be taken into account with the tool in an automatic manner. After that, we will perform a static analysis and we can perform dynamic analysis as well. If we focus, well, the whole portfolio for dynamic analysis is quite big. So we can perform harmonic analysis, which is more focused for turbomachinery. But if we think about, for example, PCBs, something very important is the natural frequencies of the structure. So modal analysis is going to be a must. Random vibration is going to be very important, as I will show you in the next slides. And explicit dynamics is going to be another type of analysis, which is going to be really important for evaluating impacts in my PCBs, drop tests, for example. All right, so think about, for example, a PCB or an electronic device in general, which is inside a car. There are many actually inside a car nowadays. Think about the vibrations that this PCB is receiving during the whole life of the product. So for this, we need to take into account how to quantify the vibration in my structure, and not only quantify it, but also to calculate how much is going to be the deformation because of these kind of vibrations. And also, eventually, we will end up with calculating the fatigue life of the product. So for vibrations, obviously, a transient analysis is not an option. Why? Because if you think about the car going through the road, the first time it's going to receive one type of vibration, but the second time is going to be similar, but not the same one, right? The third time is going to be different as well, and so on and so forth. So it means that we need to perform not a deterministic analysis, but a probabilistic one. So starting from the time history, what we are going to calculate is the PSD solicitation, and this PSD, or power spectral density, will be introduced in my structure in such a way that with ANSYS Mechanical, I will be able to calculate the response power spectral density of my device. And after this, what we can do is directly calculate, by using sigma values, we can calculate the fatigue life due to this random vibration part. So this is a very powerful tool for calculating fatigue because of the vibration of my PCB or my electronic device. Okay. So this random vibration is going to be one of the most important type of analysis that we will perform from the structural point of view, that we will perform to our PCBs. Another type of dynamic analysis will be what we call drop test. So think about, for example, this PC board that you can see here, and you want to simulate what's going to happen in the case of an impact. Or for example, this mobile, which is also dropping onto the floor, or this laptop here that you can see in the bottom part of the slide. So this is actually what we can perform, another type of dynamic analysis that we can take into account by using ANSYS, and it will be a drop test, and it will tell me how the structure is going to break actually because of the test of the drop. And also we can impose like different heights, different distance to the floor, different velocities, different type of components, materials, etc. So this is another very important type of dynamic analysis that can be taken into account for electronic devices. But I will say one of the most important type of analysis that we need to perform in PCBs or in electronics in general is what we call thermal analysis. So with ANSYS, and actually I will come back to this in the next part of the presentation, we are able to calculate from steady-state thermal analysis to transient analysis. So, for example, for PCBs, something very popular will be to perform a transient analysis where we will get a curve over the time when the electronic device is being on, so it's heated up, and then it is off and it's cooling down. So we will get this cycle of temperature, and it will be calculated by performing what we call a transient dynamic analysis. I have to say here from this point of the presentation that there are two ways actually for calculating the temperature profile of my PCB. One of them will be by using computational fluid dynamics, so by using IcePack, as I mentioned before. So by doing that, by performing that kind of analysis in a CFD analysis, we'll be able to calculate the temperature of both the fluid surrounding my structure as well as my solid structure. So I can calculate that temperature profile in IcePack. Another option is, okay, I don't want to calculate the fluid domain, but I can take into account each effect by using different conditions, like for example, convection. So if you know the field coefficient of the fluid surrounding your structure, in that case, you can do a simplification. You can do an approach where inside ANSYS Mechanical, you can calculate the temperature profile of the solid part. So you can impose different temperature profile, you can import different heat flow, internal heat generation in case you know that value, radiation in case you have also this kind of phenomenon. So you can calculate the whole temperature profile inside the same tool, which is called ANSYS Mechanical. So you can perform a steady or a transient thermal analysis of the solid part, and you will take into account the fluid surrounding your structure by taking or by considering different boundary conditions. This is one option, and as I mentioned before, the second option, the most advanced option, is to calculate the temperature profile for both, for the fluid and for the solid part, by using a computational fluid dynamic analysis. In any of both cases, even though you go through the pure ANSYS Mechanical option, which is the one you can see in the slide, or if you go through ANSYS CFD analysis, in both cases, what you will need is to transfer the temperature profile as a boundary conditions for the structural analysis. So this is what will be done actually with this link that you can see here. So automatically the temperature will be imported in the mechanical analysis, and so you will be able to calculate total deformations, bomb missile stresses, fatigue life, vibrations, etc., because of the thermal boundary conditions. Okay, so I just wanted to highlight this part. We can go through both ways. CFD analysis, more precise, but I need to do an extra analysis for the fluid domain, or purely ANSYS Mechanical, where I calculate the temperature profile by taking into account some assumptions for the fluid surrounding my structure. Both options are available. All right, let's go now more deeply in PCBs. So as I said before, one of the most important analyses is the thermomechanical actually performance of the PCB. So let me show you what will be the workflow actually. The workflow, if we go through from A to Z analysis, the workflow will be, we will start in an electromagnetic analysis where we are imposing some electric, or actually we can calculate the electrical currents in my PCB actually, and because of these electrical currents, because of the Joule effect, I will be able to calculate the thermal or the temperature profile in my whole PCB. So this will be what I mentioned before of a two-way fluid structure interaction, because as long as the device is heated up, maybe I will be more losses, heat losses, so electrical losses as well. So I will be in a loop. And once I arrive to the final temperature profile, then this will be the input for my structural analysis. So I will be able to perform what we call a thermal stress analysis. So up to here, this is the whole workflow that I mentioned several times during the webinar. Now, let's think about a PCB. Let's just spend just 1 minute about thinking about what is a PCB. If we think about a PCB, what we have? We have stack-ups. Okay, so we have layers of different materials which are forming the PCB. This is a combination actually of the electric material as well as metals materials. Typically, we will use coppers. So we have let's say we have several layers which are forming my PCB. Okay, what else do we have in a PCB? We have trace, right? Because the signals have to be routed along the layer, along the metal layer. But since we don't have only one layer, but we have more than one layer, we have bias. We have vertical interconnect access between all layers. So with the trace, we are let's say spreading out the signal through the layer, and then with the bias, we are transmitting this signal across all layers. For this, typically, or in the industry, they use what we call ECAD, electronic computer-aided design representation, or data and geometry. So in other words, there are specific tools out of ANSYS, like the ones you can see here, Cadence, Allegro, Altium, Designer, Mentor, for Expedition, PAD, etc., where these are specific tools for creating these PCBs, layers, trays, etc. Now, what is the idea? If we think about speed versus accuracy, the first option, or something which was used traditionally, let's say, we can perform or we can create a lumped board properties approach of my PCB, which means in terms of accuracy, it's not going to be that accurate, but it will give us velocity. Why? Because actually what we are doing is just we are imposing equivalent material properties, like orthotopic properties for in plane, for normal to the plane. Obviously, we are not taking into account the proper representation of the trace. We are not taking into account the bias as well. So essentially, what we are doing is just creating a box, small box, as I will show you later on, a thin box actually, and we will impose equivalent material properties. So we will get obviously an approximate solution, but obviously it's not the most accurate one that we can perform. Now, if we think about which one is the most accurate one that we can perform in PCBs, in that case, we have to model the whole geometry. So we have to model the traces, we have to model the planes, the layers, we have to model the bias. Obviously, this is the highest accuracy that we can get. But as you can imagine, first, the engineering part for creating the geometry is quite high, obviously. And then the mesh, boundary conditions, etc. It's going to take a lot of time. So yes, it's very accurate, but the speed is going to be almost, maybe once we have these quantum computers in the future, we'll be able to use this approach. But as of now, this is not an option. So what we call the ECAD approach is something which is in between both worlds. So it's giving us a huge accuracy, but we are not having a penalty in the speed, actually. So what we are doing, and I will show you later with more information, we are just creating a simple mesh, creating a simple representation of the PCB, and we will map the metal fraction of each layer coming from the ECAD data. Okay, so this is actually the one that we are going to focus more during this presentation. So as I said before, imagine, for example, this Galileo board. This Galileo board has around more than 3,400 bodies inside. And we are talking about micrometers. So think a little bit about that, okay? How to create the geometry of this, how to measure it. So the traditional approach, as I mentioned before, we will export the step file from the board layout, from the ECAD software that I mentioned before. It will take around 30 minutes in the best case, in the best scenario. Then you have to import it in our tools. We have two tools actually for geometry representation, design model or space claim. So let's say it will take in the best scenario around 10 minutes. So we have already 40 minutes only for reading the file. Now you have to do a lot of Boolean operations. You have to share topology so that everything is connected. This can take around 44 hours and still you will be doing it. Then obviously you have to import the geometry in mechanical for performing the analysis. You have to mesh it, which is the most important part here. You have to specify your boundary conditions. You have to solve. This is not an option right now, okay? This doesn't work, I can tell you. Nobody in the industry is able nowadays to do this explicit approach. So what are we proposing, or what is the technique which is used in ANSYS? In our technique, which is called trace mapping, what we are doing is, okay, we have the layout, right? Okay, we are going to create a simplified geometry and mesh. This is simple, actually. As you can see, this is just a bunch of elements. Let's say, I don't know, it will depend on how big is the PCB, but I can tell you it's very simplified geometry and mesh. We don't need something actually very advanced in terms of the mesh. Then what we are going to do is we are going to import the layout representation. And this layout representation is going to be mapped on the target mesh. So essentially, in terms of the computational solution, this is the mesh which is going to be solved. But also, we are taking into account the trace mapping because of the layout representations that we are importing from the ECAD system. And this will take, I can guarantee you, I can show you later in the demonstration, this will take much lower time for the simulation, and the results will be almost of the same accuracy than if we take the explicit approach that I mentioned before. Okay, so actually what we are doing, or what the software is doing is, here you can see the black lines are the structural mesh, the FEA mesh. And you can see in blue, for example, the software is just mapping the different material properties, if it comes from FR4, for example, for the elastomer, or if it comes from the copper, or depending on the material that you are using for the tracings. So the software is mapping the conductivity on each cell. So in other words, if you don't do this mapping on each cell, you will have the same thermal conductivity. But in this case, by doing this trace mapping, the software is going to be able to map on the FEA mesh. It's going to map the conductivity cell by cell. So that's why it's going to give you much more information, and it's going to be more accurate than if you take into account just the LAMP model. Actually, I can show you here an example of what I mean by LAMPed board and the ECAD board. In the LAMPed board, what we are doing is, okay, we are taking into account all these components that you can see here, even the fan, etc. But the tracings, as well as the vias, are not taken into account. So we are just imposing an equivalent thermal conductivity. With the ECAD board that I mentioned before, with the trace mapping approach that I mentioned before, we are taking into account all these tracings that you can see in the PCB. So if I just showed you just some results, so for example, you can see for the LAMP board, I'm getting higher temperatures values in some areas. I'm getting, for example, a better accurate heat dissipation in the ECAD board, obviously, because now what I'm doing is I'm inserting the proper and the most accurate tracings in my layer. So obviously, I'm giving the PCB more different orientations, different trace where the heat can be dissipated. So that's why the ECAD board approach is going to give you a more realistic approach than if you go to a simplified or simplification like the LAMPed board. So how are we going to do this import of the geometry? Well, the first thing is to import, to do a directly import of the PCB layers, only the PCB layers, okay? And then by using what we call external data, we are going to import the trace information from these softwares like Cadence, like Allegro, that I mentioned before, in the same format file, actually. So we just need to export the OBB file, for example, and it will be read in our external data module inside Workbench. Then what we are doing is just combining both in such a way that I can perform the static structure analysis, taking into account the trace mapping. This is what I mentioned before. The temperature profile also may come from the CFD analysis, from IcePack, and it will give us the temperature solution so that I can perform the full analysis inside ANSYS Mechanical. Okay, thinking again about geometry, you can see here, it's very simple actually, the geometry that we are importing. So the geometry will be a bunch of layers. So it's just nothing actually, it's just we just create a sketch with the cross section of the PCB and then we extrude it, that's it. This is the thickness that, depending on the thickness of each layer, we will impose. And then obviously we can include the rest of components like this heat sink, for example, other components, solder bumps, etc. So very simple, as you can see. And then the trace import in mechanical, once you import by doing this external data, once you read the trace information, it's going to be mapped already in the FEA mesh. So once you create the mesh, all thermal conductivities is going to be imported, and we can also control how many points I want to use. The more, the higher the number of points I use for the discretization in X and Y, the more accurate I'm going to get. But obviously, the longer it will take for creating the mapping of the trace. Then, once it is done, the only thing I have to do, because of these connections with CFD, with IcePack, the temperature profile is going to be already imported, interpolated actually, in my PCB, and I can apply the rest of boundary conditions, kinematic or structural boundary conditions, ball pretensions if there are. I can apply displacement, I can apply, I don't know, some kind of pressures if it's the case. So by doing this, I'm taking into account all tracings from the structure, as well as the temperature profile, which is coming from CFD. Up to this point, I wanted to mention, this temperature profile, as I said before, it may come from CFD, or it may come also from ANSYS Mechanical, in case you impose boundary conditions which are equivalent to the fluid surrounding your structure, okay? So we have both approaches. In any case, regardless of where the temperature profile is coming from, you can evaluate after that the results. So for example, here we are just cooling down from 217 degrees, which is the zero stress temperature, to the condition simulated in IcePack, where you are applying the cooling process with the fans. And you can evaluate, like in this case, I don't know, deformation across the heat sink mount. You can evaluate vibrations, deformations, by taking also into account all the temperature as well as the PSD that I mentioned before, power spectral density. We can evaluate layer by layer information, shear stresses, von Mises stresses. We can, as I said, inspect layer individually and see how is the connection between each layer. I can actually go further. I can say, look, I want to impose what we call a cohesive zone model material property in the connection between layers. So by doing this, what I'm going to be able to do is I can impose like maximum stresses that my layer is going to withstand. And after that, the software is going to debond. All layers are going to be debonded, and the contact, so the connection between layers, is going to be disconnected actually. So I will see actually what you can see in this image. I can see I will be able to see the lamination between all layers. So by imposing this CZM or cohesive model, I can actually see how it's going to be the delaminations because of the temperature profile. So after that, I can change the adhesive in case there is an adhesive. I can change the pre-stress or the pretension of the ball pretensions as well. I can evaluate it layer by layer and understand why and investigate why I'm having this delamination, which is something I might not be deciding actually for my design. More cases or more situations that we may have into account. For example, if we want to evaluate the stresses in the solder bumps, okay? So as you know, there are some solder bumps between layer of the board and the substrate. And something which is typically quite important to take into account on these cases is to, obviously we are having a, sorry, I'm having a chat connection from Rajavendra. If you want, we will keep just type your questions, whatever question you have in the chat, and I will address them in the end of the conversation. the webinar. So as I said before, we may have a cycle of temperature, and typically on these electronic devices, on these PCBs, we have these kind of cycles whenever it is on off. Okay, so we may have a different cycle or a cycle of temperature along the PCB, and because of this kind of let's say a cycle, we may have fatigue as well, fatigue problems. Also, we may have a situation with creep, where obviously because of the solder, where they have a low melting point, we may have creep problems in the solder part. Also, we may have viscoplasticity. So we can impose these material properties, and then we can end up in the situation where we want to calculate the fatigue life of these joints, of these bump joints actually between layers. So for this, in ANSYS, we can evaluate by using this, what you have here, the whole paper actually from Darboux, effects of simulation methodology on solder joint crack growth correlation. So this paper, or the correlation on this paper, has been inserted inside part of the post-processing for fatigue in ANSYS Mechanical. So you just have to provide some constant materials, K1 to K4, are material properties. So the software is going to be able to give you actually the cycles to start to have crack. Okay, so this is going to be very important in order to understand if how is the sold or the weldings between the bumpers connection between layers actually. So this kind of fatigue life can be evaluated by using, as I said before, ANSYS Mechanical. You may need to go further actually, and you may need, okay, do you need even a more accurate solution? So we can use the technique which is called submodeling. So in the technique called submodeling, what we will do is we are going to do a global analysis of my PCB, where this is called global or parent model. And then we will isolate the specific part where I'm more interested in to analyze, separate it. And the idea is that the displacement from the global analysis will be imported as boundary condition in the submodel. So then I can concentrate only on this specific part from my PCB, and I can take into account the displacement or the rest of the part from the PCB, from the global structure, just by importing this displacement value automatically in the software. This is something which is done, as I said before, automatically, and we don't need to do anything, just connecting different components, as you can see here, in Workbench, in the project schematic. So by doing this, I will use the submodeling technique, and I will be able to focus only in my area of interest. All right, so just before finishing and going ahead with the demo, I just wanted to show you not only cases about PCBs, but also about microelectromechanical devices, because they are also important in the semiconductor industry and in the electronic industry in general. So as you know, MEMS, microelectromechanical devices are made, well, first of all, they are very small. So we are talking about micrometers thickness devices. They are widely used, I would say, in the industry for different situations, like for a fan, like you can see here, this piezoelectric fan, for piezoresistors, as you can see in this case, in this image in the right side. So there are many type of applications actually where simulation can be of use. For example, if we think about thermal electric applications for bolometers, if we think about electroelastic situation for actuators, piezoelectric for creating sensors like transducers, resonators, etc. Piezoresistive type of analysis for pressure sensors as well, strain gauge, dampings for MEMS resonator. There are many type of applications that can be simulated in the microelectromechanical devices world actually. So what I want to do now in the next few slides is just show you different cases that have been analyzed actually by using ANSYS simulation tools. There is a question from right now that I will address later on, just in the end of the presentation. All right, so let me just show you one of the case. For example, case which is called microbolometers. Well, a bolometer in general is a device actually for measuring the power of the incident electromagnetic radiation. So basically what these devices are doing is they absorb electromagnetic radiation and then they are heated up. So depending on the amount of they are heated up, you can calculate what we call electrical resistance. So, or thermal conductance as well is also known. So a microbolometer is a type of, or specific type of bolometers where actually is used for thermal cameras. And we are talking about something about micrometers actually of the length of these devices. So here you have an example where actually ANSYS is used for performing this type of analysis. We are applying some kind of temperature on this device, and then you can calculate the temperature distribution. So, we are applying a current, and you are getting the temperature distribution. In this case of the left side, we are applying 10 milliamperes, and you are getting the temperature distribution. And then what happens if you apply 35 milliamperes as a current? How is changing the temperature? So according to this, you can change different, you can evaluate different shapes, you can evaluate different material properties, and in the end, it's going to give you the thermal conductance of this microbolometer, which is the one of the design criteria that you need to take into account whenever you are manufacturing these devices. Another example would be a thermoelectric cooler. So typically how it works is that it is using, it works with a principle known like Peltier effect. In the Peltier effect, the cooling occurs when a small electric current is passing through the junction, of two dissimilar thermoelectric materials, okay, which is called like P-type and N-type, negative semiconductor. So basically what we have is a cool side, which is the heat absorber, and we have the hot side, which is where the heat is going to be rejected. So we can apply some currents actually in the what we call this part of the blocks. Actually, Peltier blocks is the name. And then we can, by using simulation, we can get the temperature distribution. We can get the current distribution, how is the electric potential, and by doing so, we can change the design actually of the blocks, or we can change the boundary conditions and see how it's going to act this thermoelectric cooler on my device. Okay, so this is another type of applications that we can take into account, in this case for thermoelectric coolers. More situations that we can take into account, some kind of thermoelectric actuator, like in this case you can see in this example. So basically what we are doing is we are applying a different voltage, 0, 15, and we will be able to see how the current is going through from one terminal to the other one. And because of this current and because of the Joule effect, we will have a temperature distribution. And after that, because of the thermal distribution, we will be able to have, we will have actually thermal strains. So the actuator is going to move. So this is a complete, let's say, multiphysics analysis where you start by imposing a current or a voltage difference in your device, and you can see how the device is going to be moving. It's going to move. You can see actually here the difference between the simulation actually and the real model. Okay, the results match quite in a very good manner actually. Also thermal electric switch. So we are following actually the same principle than before, which means we are applying some currents in our device, and we can see how, because of the thermal strains, it will move and it will touch this part, the top part will touch the lower part, and the current is going to be moving from one side to another one. Another type of thermal electric analysis that can be performed by using ANSYS. All right, more cases. This piezoelectric fan that I mentioned before. So this device typically is used for cooling electronic components. So typically they consume less energy than the conventional fans, and they have also a low magnetic permeability. So they are quite suitable for being used in high magnetic field components. For this case, what we are doing actually, we are causing, or we are provoking, we are causing that the device is going to be in resonance, and that's why it will start to vibrate. So basically what we have is a elastomer material here, two layers with different materials, actually, two layers of piezoelectric ceramic, which are bonded, and they have opposite polarity, actually. So in the moment when an electric potential is applied across the piezoelectric B-morph, actually, which is the name of this device, so we will have a large bending motions generated, and it will cause actually the movement of the blade. Okay. So you can see actually in the next slide, once we applied 120 volts at 60 Hz of frequency, you can see actually once we fix the structure here, how the fan is going to start to move. Okay, so we can actually, in this case, it's driven off on a alternate current of 120 volts, but you can just change actually this is just an input, a boundary conditions that you are applying, and you will see how it's going to be how by changing the voltage actually the resonance is going to change as well. So after that, you can evaluate materials, you can change the thickness, maybe you want to move it in a higher frequency, so you can change the voltage and so on and so forth. Just before finishing, another case of, in this case, is a transducer. So what we are doing here, we are placing 4 piezo resistors along the perimeter of this square thin film diaphragm. So there are 3 sensors actually connected with kind of an electrical bridge in order to measure the amount of mechanical pressure that you need to apply to the surface. So based on this, based on the deformation, what we want to do is to calculate the differential voltage. So we can actually take into account, in this case, for example, one of the output that the software is going to give me is based on the pressure that you are applying, it will give me the voltage that I need to take into account for this transducer, actually. There are many cases like this. There is another one, actually, this elastomer, where I want to apply a voltage between the electrodes. So by applying this this voltage difference, what I'm going to do is that something which originally was unfolded, as you can see in the right side of the image, will just start to deform and start to touch actually the rest of the layers till being closed. Okay, so this is an example actually of electroelastic results, and depending on the voltage that I'm applying, I will see that it will close more and it will apply a bigger pressure, etc. So another, actually this is the last one example of elastomer actuator. All right, so conclusions about ANSYS strengths. Well, ANSYS solution help to predict reliability for different analyses in a PCB life cycle, as I showed you in the previous slide. It's basically a multiphysics analysis. So yes, you can do everything with only ANSYS Mechanical. You can just perform the structural analysis, and also you can take into account the thermal response. But if you want to go more precisely, more accurate with the results, in the end you will need to perform a multiphysics analysis in which you will start with electromagnetic analysis, then you will calculate temperature profile in CFD, and then you will end up calculating the structural response in the FEA or finite element analysis. But everything will be connected in the same environment, which is actually one of the most powerful situations. The whole domain will be connected, and the tool will be able to communicate actually between all type of analysis. There are many automated scripts, templates. There are what we call customization. You can customize the tool actually, so that it will make easy to simulate all this type of interconnected analysis. So for startups, it will help you to simulate more cases or having more designs at the same time. And obviously the idea is to reduce the time to market. All right, so this is everything from this PCB or semiconductor part for the part of the presentation. So what I want to show you now, we have now around, let's say 30 minutes in which I would like to show you, well, we have a little less because we will have some questions after that. So let's say around 20 minutes, where I want to show you actually on live a demonstration of using the software for, in this case, is for a PCB actually. So as I said before, any questions you have, please just type it in the chat, and after this demonstration, we will deal with it. All right, so I have here ANSYS Workbench. Sorry, I'm just sharing. Yeah, I believe you can see now the the interface ANSYS Workbench. So this is like our starting point for our simulations. So as you can see in the left side, we have a lot of different analysis that we can perform, going from CFD, high frequency for electromagnetics, Maxwell, which is used for low frequency, PI for power electronic interference as well, Simplore, static structural. So here you will see like different components. So depending on wherever you just drag and drop to the project schematic, you will start actually to perform your analysis. So for this simulation, what I want to do first is to perform a thermal steady state analysis. So as you can see, in the moment when I just drag and drop the analysis to the project schematic, I have all the steps that I need to perform for simulating my case. So it means I need to start imposing engineering data or material properties. Then I need to have a geometry. I need to create the mesh after that. I need to impose the loads as well as boundary conditions. Then I will solve and I will post-process. So everything is from A to Z. The software is going to guide you through the simulation process. So the first thing I want to do here, and first of all, why I'm just dragging and drop a steady state analysis? Because I want to do a thermal analysis of a PCB. As I said before, the goal of this thermal analysis is to get the temperature profile in my PCB. But I could go further and say, instead of calculating the thermal profile in ANSYS Mechanical or in this environment, I'm going to calculate the thermal the temperature distribution of the fluid as well as the solid part. So I can do this, I can do that part by performing first a computational fluid dynamics. For this demonstration, I'm just going to calculate the thermal distribution by using ANSYS Mechanical, so by using only the FEA or finite element analysis. Okay, that said, I'm going to double click in engineering data. So here I can define my material properties. So what I'm going to do, I have a library of materials, which comes with the software. Whenever you install the software, there is a huge number of material that you can use here, depending on your analysis. I have one which is a customized one that they call engineering data. This is one of the things you can do. You can just create your own library of material. So in that way, you will share this library of materials with the rest of engineers in the organization. And in this case, what I'm going to do is, okay, I want to use FR4 for the layers. I want to use also components material, which is a specific one I created. TIM is a specific one I created for these devices. And aluminum alloy, for example. So by doing this, structural steel, it was always there because it's the default material. So I have a bunch of material that I can use for my analysis. So I'm just including them in my project. This is the only thing I'm doing whenever I click in adding them to the simulation. So by doing this, they are ready to be used after that in my further analysis. All right, so now I have the component called here geometry, where I'm going to import a geometry that I have already created before, which is called Mech PCB. If I can just show you actually how it looks like. I actually will show you later on in the mechanical component. But what I'm doing now is I'm just importing the geometry in my project, okay, in such a way that maybe I'm interested in to simplify how the geometry is created. Sorry, it was open in the other slide, the other screen. So maybe here I was just to, I don't know, I want to make this part maybe bigger. So, or I want to remove the bolts, or I want to change the shape of the PCB. Any of this type of cut repair or cut simplification, etc., I can do it in this tool, which is called ANSYS Workbench. ANSYS SpaceClaim. For this case, actually, I just imported this geometry from another cut tool, and then I can continue working on preparing it for my analysis. But as I said, you can also create the geometry from scratch. Okay, so I'm gonna close a space claim because I'm gonna work with this geometry. So the next step actually is to open the analysis tool, which is called, as I said before, ANSYS Mechanical. And with ANSYS Mechanical, I can just, as I'm gonna show you now, the tool, what it's gonna do is gonna import the geometry from a space claim automatically. I don't need to save, I don't need to do it manually. The only thing I need to do is to specify what is the file, that's it. So what the software is doing now is just reading the geometry from space claim and importing it back to ANSYS Mechanical. All right, so this is the same geometry that I showed you before. So you can see that there is a heat sink here. I can just hide it just to show you the component inside. So there is a bunch of bolts which are connecting my in this case the heat sink with the main part or the layer actually of the PCB. I have some components here, different components which are connected to the main part of the PCB. And obviously I have this, so all bodies. I have this part here, which is the heat sink. It's the part which is where the heat is gonna be synced on my device. All right, so the first thing I'm gonna do is, as you can see, it is just respecting the names from space claim. So I have these 5 bodies here, which I called beforehand, I call it TIM, teams. So I'm gonna insert, I'm gonna assign the material, which is called TIM. So I select it, all right, that's okay. The other thing I'm gonna do is, there is this component here, which is called Mech Solid in this case. I can change the name at any time. So this is the heat sink, actually. So for this one, I'm gonna use aluminum alloy. Then there are these components. I can show you if I hide this body. There are these components that you can see here. All these bodies. So these components, I created a material, which is called component, and I'm gonna assign this material. Then there is the PCB itself. I'm assuming in this case that is FR4 material. As I said before, what I'm doing here is I'm using the lumped approach, but in the next example I'm going to show you, I can do the same for the trace mapping. In this case, I'm not mapping any trace, etc. It's just to show you the workflow for performing a thermal and a structural case. And then I have these bolts that I can assume that all of them are just structural steel. So this is the material actually by default, which is used for these bolts. All right, I'm gonna show all components. Great. The next thing I have is the connections between geometries. This is what I mentioned before. All connections, all contacts between the geometries are detected automatically. And this saves a lot of time, trust me. Otherwise, you have to go and manually define the contact body by body. So if you think about this case, it's a simple case which has almost 48 connections. So you can imagine how tedious it might be to create the contact between all geometries. So as I said, this is an advantage of the software because it's going to be able to detect them automatically. What I can do here is just rename based on definition. So it will be simpler for me as long as I'm just creating a name for my bodies. It will be simpler for me to identify which contact is being used for each part of the PCB. And also it will allow me directly to see, okay, from this mech, from this to this PCB part, which I can see here in red and in blue, this is the pair of contact. Maybe I want to change this contact and I don't want to use a bonded one. Bonded means that everything is connected. I will use, for example, a no separation one, which means that I'm allowing both surfaces actually to slide between themselves. So I can go individually and I can check for each of them. I can check and I can see, okay, this contact is going to be in this type, this other contact is going to be of another type, etc. So I can just go one by one and check and say, okay, I want to change it. I'm going to allow separation. I'm going to include the lamination properties, etc. This is something I can include contact by contact. All right. So once I'm happy with my contacts, the next step is to create a mesh. So I'm just right-clicking mesh, generate mesh. Just for the demonstration, I'm going to use by default mesh. I know it looks a little bit that it can be refined, but I just want to have a mesh so that I can later on, so that I can perform an analysis. But in case of if you want to refine the mesh, there are many controls actually under mesh where we can insert them and I can refine them, and the software is going to refine automatically the mesh based in my inputs actually. So I have a lot of considerations, approaches, options that I can use here for refining my mesh. Okay, as I said, I'm gonna assume that this mesh is the one I'm gonna use. So it means I'm happy with that. So the next thing I'm gonna do is the thermal analysis. So for the thermal analysis, as I said before, you have all these surfaces actually that you can see here, all these surfaces, which are actually touching the air. So what I'm gonna do, I'm gonna select them all as I'm doing here. Okay, I have almost all of them selected, these 61 surfaces. And because I'm gonna perform the thermal analysis of the solid part, but I want to take into account also the fluid surrounding, what I'm gonna do is I'm gonna insert a convection load. So right click, insert convection. And then here, this is something you need to know. You need to know how much is the fill coefficient. In this case, I know that the value is for the air is this value. So I can directly use this value. Now, up to this point, if you are asking yourself, okay, but I don't know this value, how much is it? How can I approach it? Then you need to do a CFD analysis, as I mentioned before. So with a CFD analysis, with IcePack, you will calculate the temperature profile of both the solid and the fluid side. So you don't need to include an equivalent boundary condition because this fill coefficient, this convection is already taken into account when the software is finished, when the software is solving the equation system. So in this case, as I said, I'm not going to perform the CFD analysis, so I'm just taking into account each effect, the effect of the fluid in my structure by inserting a convection load. All right, now there are more components. If I just hide this body, you can actually see that there are other bodies where actually they are being heated up because of the currents which is acting on them. So what I can do in those situations, I can insert like different, what we call an internal heat generation, so that I'm going to insert on these bodies, on different bodies, I'm going to insert this internal heat generation. So if I just to show you it, sorry, just to show you it like in here. For example, on this body, I'm going to say I have an internal heat generation of this body. You know how much heat is being generated, so you can apply it. Okay, I can continue in the rest of the bodies. So for example, let's say I have another internal heat generation here on this body, and I know this value, so I insert it. I can go to the rest of the bodies, and I'm just taking the result from another table. So I have here internal heat generation of this value, but by millimeter to the power of 3. Same, for example, for this body, I want to do the same, internal heat generation, and I have this value. Another one for this body here, so insert heat generation. As I said, I'm just taking the values from another table, but this is typically information that you have, how much internal is being produced by your component actually on each case. Okay, so by doing this, I'm just inserting an internal heat generation in different components, as you can see here, in all these components, and inserting different heat sources for my device. Obviously, since everything is connected, once I run the simulation, which is what I'm going to do now, I'm going to click in solve. So what I'm doing actually, if I show all bodies, there is an internal heat generation of these components, and from the other side, on this body, I have an internal heat sink, which is being evacuated from my device. So because of this, I can calculate the temperature profile. So the solution has finished. I just click in solve. The solution has been finished now. And what I'm going to do is I can insert, for example, temperature profile. Let's say in my domain, maybe I don't want to show the mesh. So I can directly already see how is the temperature profile. Maybe I want to go body by body. So let's say, for example, I want to go to this body. I want the software to show me the temperature profile. So by doing this, I can see which areas are being heated up more rather than the others. I can, for example, let's say I want to evaluate, for example, the total heat flux on, let's say, for example, this body. And by doing this, I can see only on this part how the heat is being evacuated from the hot areas actually to the cold ones by the heat sink actually. Maybe also I want to evaluate how much heat is being evacuated. So I can just drag and drop the convection boundary condition that I applied before. And I can see how much heat, 1.75 watt, is being evacuated or is being going through this heat sink that I have made of aluminium. Okay, so by doing this, I can evaluate my results. Obviously, after that, I can change the designs, I can change the boundary conditions, I can change the shape, I can play with that and run again the simulation. So the whole process is going to be persistent and consistent. All right, so now I have the temperature profile in the whole system, and I want to calculate how this PCB is going to be deformed. So what I'm going to do now, I'm just coming back to the project. I'm coming back to Workbench, and I'm just going to drag and drop a static structural component, and I'm connecting it, as you can see here, I'm connecting it to the thermal analysis that I have done before. And what I'm telling the software is, look, the solution, so the temperature that you have just calculated, insert it as a boundary condition for my structural analysis. So if I just come back to Workbench, sorry, to ANSYS Mechanical, you can see that I have now a new component, which is called ANSYS Structural. And in this new component, what I have now is imported body temperature. So this imported body temperature, I can just evaluate. And these are the temperature values which are coming from the thermal analysis that I have performed beforehand. So as I said before, you don't need to, let's say, you don't need to take the values of the temperature from one mesh, from the thermal analysis, interpolate it in another mesh. No, this is no longer necessary. Automatically, the software is clever enough to take the temperature from the thermal analysis and impose them in the structural one. So I have the temperature, but now I can impose more boundary conditions. For example, let's say I have here my PCB, and I just want to fix the structure so that it doesn't move. So what I'm going to do now in this situation, I can just select, for example, this vertex, and I'm going to insert, I'm going to say this vertex is fixed supported. So that vertex is not moved. The only thing I want to do now is to constrain the structure, because I'm not going to apply any pressure, I'm not going to apply any displacement given value or any force. I just want to evaluate how the structure is going to deform because of the temperature profile. So I'm just constraining some part of my structure, for example, some vertices, like in this case. I'm going to assume that, for example, in X, it cannot be moved. In Y, it cannot be moved. In Z, I'm constraining the movement. And I'm going to constrain just some degrees of freedom from the other side. So in such a way that, for example, in Z, this is fixed. As I said before, I just want to fix the structure. I just want to evaluate how the structure is going to deform because of this temperature profile. But now there is something else that I need to take into account. As you can see here, if I just hide the sink, I have a lot of bolts, and these bolts actually are pre-stressed. So what I'm going to do now is, let me just hide also this body. I'm going to say, look, on this surface, on this cylindrical surface, I'm going to insert what we call a bolt pretension. In this bolt pretension, what I want to simulate actually, what I want to simulate is, I'm pre-stressing, when you manufacture this device, what you do is you pre-stress the screws, so you are applying a pre-stress, and then you place it as in the normal working behavior, so it will start to work and it will start to heat it up. So for this, what I'm going to do is, I'm going to assume 2 load steps. So I'm selecting 2 load steps here. And I'm going to say, look, this temperature profile is going to apply in the end. Why? Because before, in the bolt pretension, I'm going to apply a pre-stress, only a pre-stress, without any there is no any other load acting on my structure, even there is no any thermal load. So I'm applying a 100 newtons load on my structure, and then for the second, third, fourth, and so on load step, I'm locking the pre-stress. Why? Because after, in the second load step, what I'm doing is I'm applying the temperature profile. All right, so now, obviously, you can see that I have 16 volts. So what I'm going to do now is, I don't want to apply them all manually. I'm just going to create a name selection for this surface, and I'm going to call it volts, for example. Sorry, not like that. I'm going to repeat the process. I'm going to create a name selection, which is going to be called volts, and I'm going to say, apply this to the items with the same size. So by doing this, if I click in OK, it has created, as you can see, name selection of volts for all the rest of the volts. What I'm going to do now, I have this volt pretension. I'm going to use our object generator, which is used for creating a pattern for duplicating entities which are already created in the tree outline. And I'm going to say, look, the volt pretension load that I created manually before, you are going to duplicate it in the name selection that I created called volts, individually, entity by entity, so on each entity. Click on generate, and you can see now all of them have been generated automatically. So I don't need to go one by one because it will be very tedious and I will lose a lot of time on them. Another thing I can do is I can select them all and I can group them and say these are my volt pretensions. All right, I can close the object generator. So what I have here is a lot of volt pretensions that have been already generated automatically by doing this process that I just discussed. All right, so I have volt pretensions. I have fixed support. If I just show all bodies, I have fixed support in different parts of the structure, as well as some, I have just fixed some part of the structure. And I have an imported body temperature on my body, okay, for the time step 2. So now I have everything to solve my case. So I right click in solve. And the software is just solving the equation system. It's applying all the boundary conditions, and it's giving me a message here that it will suggest you to use at least more than one element across the thickness, but this is just for a demonstration, so it's okay. All right, so once I finish, what I can see now, I can just evaluate, for example, total deformation in my structure. I want to evaluate maybe equivalent von Mises strain on this part. I can just evaluate the results. So for example, what can I see here? This is the total deformation because of this load, temperature, and volt pre-stress that I'm applying in the system. I can create a video, and in the video you will see first, let me just play it with more time and with more frames, 40 frames maybe. You can see at the beginning, it is receiving only the pre-stress. This is what is happening now. It is just pre-stressing the volts, and now the thermal strain is going to be calculated because of the temperature profile. Obviously, even though you can see that here it is a little bit over-scaled, you can just change the scale here, and you can say, no, show me the true scale. You can see that the true scale, the device is not being deformed that much. Okay, so I can evaluate again the video, and I can just play with it and see how the structure is being deformed because of the application of both the pre-stress as well as the temperature profile. After that, I can just change anything beforehand. So let's say, for example, if I come back to Workbench, let's say I don't want to, I want to extend, for example, the length of the heat sink, for example, and I want to see how much heat is going to be evacuated now because of the change in some part of the structure. So what I can do is I can just open a space clean, as in this case, and I can, for example, select these components, all these, let's say the length of this component. I can select them manually. Tag, 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 and tag. And I can say, okay, I don't know, I'm going to pull it. I'm going to make it bigger, like in this case, something like this. So what I have done is I just changed the geometry. I just changed the length. So if I can just close workbench, space claim. And what you can see now is that the software is telling me, look, you have changed something upstream, so you need to refresh the information in Mechanical. So this is what I'm saying now. Yes, read the updated information. And once I do that, what the software is going to do in Mechanical is just going to read the new geometry, which is what it's doing, is going to do now. It's going to read the new geometry, import the geometry, which is what it is doing now. And after that, as you can see here, now it is telling you the mesh has been kept for some geometries because they didn't change. So it allows you to, you don't need to mesh again everything, only those parts which were changed actually. And then you can just do the same. Okay, now I have a different device, update the whole project. And as you can see, all the boundary conditions and loads that I inserted before, everything is remaining. So the software is clever enough to calculate again the temperature profile for this new device. You can see how everything is changing. The temperature profile, the reaction proof, the heat is the same actually because we didn't change the heat sinks. And then you can evaluate the temperature, the total deformation, equivalent elastic strain, etc. because of this new configuration. All right, so this is what I wanted to show you in terms of what we call before a lumped analysis. From A to Z, we are performing a thermal analysis, and we are ending up with a stress analysis, actually. What I want to show you now, before going to the question and answers, is this case that I have before. I'm just going to show you the case from here. So actually what we have done here is we have imported from this module, which is called external data. We have imported a file, you can see here, which is ecatutorial.tgz, which contains information from OVV files, from these ECAT tools that I mentioned before. So you can use Cadence, you can use Allegro, etc. And you can import the trace mapping from those CAD systems or ECAT systems. After that, what we have done here, if I just open SpaceClaim, I just want to show you the geometry. So you will see that this is quite simple geometry, actually. So we have created like different layers, as well as other components from the PCB. So this is actually what I'm trying to show you now. So actually, if I just show you, you can see from this PCB, basically what we have is, well, this part is not taken into account for the analysis, so this is what we have. Only the geometry is as simple as different layers with the piezoelectric and the FR4 material, as well as the shape. So this is very simple, actually. It's just a simple representation of the PCB, and the only thing you have to do is to create the layers. You see? Okay, so now, if I just open this part, what we have done in, sorry, not this case, this one. What we have done is, these are the components so that I have imported from SpaceClaim. So I have to impose the material. If it's a dielectric, you insert the dielectric. If it's FR4, you insert the FR4. It depends on the material that you are using. And then this imported trace, this is where it is coming from, in this case, Allegro. So basically, what you can see here, if I just show you it, this, what we have here is the trace mapping, which is taking into account the thermal conductivity of the tracings, and it is being mapped on my mesh. If you check in the mesh, sorry, let me just mute everybody. If you check in the mesh, actually, the meshing is nothing, actually. It's very, if you try to do this, the mesh for these actually tracing mappings, you will need to have a very, very refined mesh, where in this case, it's almost nothing. We are talking about how many elements? We are talking about 3 million elements, which is calculated actually in no more than half an hour, actually. So by doing this, as I said before, we are importing the tracing. And as boundary conditions, we had just applied 50 degrees temperature for everybody, for the whole bodies. just to simplify the case. Also, you can import this temperature profile with the trace mapping coming from IcePath, from the CFD analysis, so it will be even more accurate. And then after that, you can evaluate total deformation, like in this case. You can see actually the degree of detail. You see here the degree of detail for all layers, okay? Directional deformation as well. You will see like how is the deformation in one certain specific direction, in this case in Z. You can evaluate also equivalent elastic strain, as you can see. Obviously, this is impossible to get this grade of detail. It's impossible to get actually in a lamp analysis as I did before, okay? So the finer the mesh you have and the more points of discretization you use in the imported trace, in this case I used 400, the more you use, the more accurate information you are gonna get actually for the final response.